Thanks. I'll begin with a word of prayer. So, what happened? He's taking over? Did you do it already? What? I mean, but have you already taped before? No? Okay, well then I guess it's okay. Sorry. Whatever. I'll begin with a word of prayer. Sorry. Dearly Father, we thank you for this day. Thank you for these students. Pray that you just help us today to understand a little bit more about your creation, about partial fractions, and just to wrap up any remaining homework questions there might be about trigonometric substitution. In the name of prayer, Lord Jesus. Amen. I will begin by just reaping the rewards of last class's discussion. So the first question people had earlier today, and you guys probably also have this question when you think about it, is number 60 from section 8.2 asks you to calculate the volume of a solid of revolution where you're revolving y equals x times sine of x from 0 to pi around the y-axis, right? Anybody in here had a question about that? All right. So I figured as much. So let's talk about that. So to do that, if you were to try to use the method of washers, you'd get into trouble because the inner and outer radius would both be governed by this one graph, right? So it's kind of a pain if you tried that. So the way to do this is by the method of shells. That's section 6.3 in the book. We do cover it in Calc 1. Some of you didn't have Calc 1 here. Whatever, it's okay. Let's talk about it now. So what you do is you think about taking this shape and like parsing it, chopping it up into a bunch of cylindrical shells. I would say like an onion, but onions don't really have cylindrical shells, right? Unless they're grown really weirdly. So I just think about, chopping this into a bunch of concentric cylinders. So the thickness of each cylinder would be dx, right? The radius of the cylinder would be x. Here's a picture of it. And now the height of it would be what? Right, the equation, it would be y, where y is equal to x sine x. So if you take this cylinder, this infinitesimal cylinder, right, it's infinitesimal because its thickness is infinitesimal, its height and its circumference are not. You could lay it flat into an infinitesimal slab with, length 2 pi x and width x sine x. So the area is 2 pi xy, and the thickness is dx, so the dv, the infinitesimal volume for such a slice, would be 2 pi x squared sine x dx. So you can do this from 0 to pi, then you just add them up to get the volume. Does that make sense? So you have my sympathy if you're trying to do it with the other method, with the washers. Yeah, no. No, don't try to do that. These are another, I said I'd give you a couple more examples of how to set up the trig substitution. So here's number 31. It's x times 6x minus x squared minus 8. So what I'm saying here is to do this one, I want to eliminate the radical, right? So I rewrite this as minus x squared plus 6x minus 8. Last time I showed you how to do a little bit of completing the square, but the completing square problems we had, they had an x squared, right? So we didn't really face the issue of what to do if x squared has something multiplied last class. If x squared has something multiplied, just factor it out is my advice. So I just factored out the minus 1 because I like to think about x squared with a 1 in front of it when I complete the square for my convenience. So factor out minus 1. That makes the 6x become minus 6x. It makes minus 8 become 8. And then I can complete the square. So that's x minus 3 quantity squared. Writing this adds 9. I only had 8 up here, so I have to subtract 1 to be fair. And then I multiply minus 1 back through, I get 1 minus x minus 3 quantity squared. And if we're going to use a trig substitution, if I have a constant squared minus the variable squared, that's a sign substitution. So I set x minus 3 equal to sine theta, and then I just have to plug that in, right? So x, for example, is what? X, if you solve for x, you get sine theta plus 3, which is this, right? So x is 3 plus sine theta. The square root simplifies to cosine theta, right? And the dx gives me another cosine theta d theta. So to do this integral, I can do this corresponding trig integral. So there's another start to a trig substitution problem. I'm not going to finish it, but that integral's not hard, right? You've got like a u substitution for the sine times cosine squared. You let u equal cosine, and then 3 cosine squared. That's a cosine squared integral you can also do. It's not a big deal. Any questions about that before I talk about 34? Okay. Again, to deal with this, I have to complete the square. So x minus 2x plus 3 is x minus 1 squared plus 2. And if I have a sum of squares, that suggests a tangent substitution. In particular, I let x minus 1 equal square root of 2 tangent theta. Why do I do that? Well, the reason I do that is because if I do that, x minus 1 squared plus 2 is really 2 tangent squared theta plus 2, which is 2 secant squared theta. So we plug that in here, and we get square root of 2 secant squared theta. X, well, solve this for x, you get x is what, 1 plus 2 square root of 2 tangent theta, so this is the x, right? And then, of course, the differential dx is square root of 2 secant squared theta d theta, because the derivative of tangent is secant squared. Again, this falls under the general umbrella of advice I gave with that table of possibilities last time. Yes, sir?
Where did you get the cosine theta times cosine theta from?
Sure. The first cosine theta, this one, is from the red. So that's from the square root. The square root of 1 minus x minus 3 squared is what? It's the square root of 1 minus sine squared theta, which is the square root of cosine squared theta, so it's just cosine theta. So that's from the square root. The second cosine theta and the d theta are coming from the dx. See, dx is equal to d of sine theta, which is cosine theta d theta, so that's this one. So one from the differential, the other one from the square root. Other questions about this? Other questions about homework then? Yes, sir. 8.2.78. Ah, yes. So for 8.2, number 78, what you want to do is to start with the integral from a to b of x minus b times f prime prime of x dx. If you start with this, you'll be able to derive it. Take that as your starting point. See, if I do that, right, I can do what? I can say, okay, so this, I'm going to call this thing u. I'm going to call this thing dv. All right? So then what I have is I've got uv evaluated from a to b minus the integral of v du, right, from a to b. This is how integration by parts works when there's bounds. The thing is, okay, so what do I have? I've got u is equal to x minus b. So du is equal to dx. dv is f prime prime of x dx. So what's v? Yeah, just f prime of x. So what we have then is we've got x minus b, parentheses, times f prime of x evaluated from a to b, minus what? Minus the integral of, from a to b, of f prime of x times dx. I'll write one more step for you, since I wrote one more step for the other section. What is this? You evaluate. What happens when you take the upper evaluation? We get 0 because we get b minus b, which is 0. So what we get is we get minus a minus b times f prime of a, right, minus the integral from a to b of f prime of x dx. And then algebra finishes it. They also give you a hint about how the integral of f prime of x dx simplifies, right? It's f of b minus f of a. So it's a combination of that hint and what I just wrote, which is integration by parts. That's how you do it. Yes, sir?
And you still find an integral of f prime of x, right?
Yeah, I'm not done. I'm just giving you a hint. Yep, yep. Other questions? I like that homework problem. I think it's very interesting. Oh, yes?
8.2, number 49.
Find the area between the graph of f and the x-axis. So we have arcsine of x from 0 to a half. It's okay if I work here? Okay. Let's see here. So roughly speaking, arcsine is what? It's sine run up the axis, right? So it looks like this. So from 0 to 1/2, we're trying to find this area, right? I'm not really sure the picture is even needed here. You said find the area under that. So all we're really asked to do is integrate from 0 to a half inverse sine of x dx. So? Yep. How do you do the integral of inverse sine? Yeah, I think so. So we'll let this be the u. Let this be the dv. So what's du? Right? And so what we have is we've got, and of course v is equal to x, right? So I've got x inverse sine of x evaluated from 0 to a half minus the integral of x over the square root of 1 minus x squared dx from 0 to a half. And I'll let you guys finish it. Yes, sir?
Now, is it okay if you don't write the bounds, but you add plus at the end until you get to that?
Oh, yeah, absolutely. If you want to find the antiderivative and then at the end apply the fundamental thermocalculus part 2, same logic, yeah. I would not object to that, no. So, what's the inverse sine of a half? Five or six, right? Sine of 30 degrees is half. See other homework questions? All right. So with that, let's start to topic of partial fractions. This is section 8.5 in your book. It's there's also again, I would encourage you to read my notes, my chapter 9 notes. I have a few examples in there which are probably helpful. So to start with, let me just talk about what's the problem of partial fractions. What's the goal of partial fractions? The goal of partial fractions, all right, is to integrate f of x, where f of x is given by p of x over q of x. Here, p of x and q of x are polynomials. I am assuming, of course, that q of x is non-zero. Right. So how do you integrate such a thing? That's the question. All right? The technique of partial fractions decomposition gives an answer to that question, as we're going to see. Before I get to that technique, though, I need to remind you what we already know. What we already know is we know how to integrate what are called basic rational functions. So remember, we already know how to integrate. If I've got, and here, and throughout this discussion, both A and alpha and beta are given constants, okay? If I have dx over x minus a, I know how to integrate that. That's a u equals x minus a substitution, right? We get natural log of the absolute value of x minus a. You guys know this, right? This should have been done in Calc 1, for example. If I have the integral of dx over x minus a squared, again, I make a u equals x minus a substitution. I get minus 1 over x minus a. Right? And this goes on. I mean, anything like dx over x minus a to any power, any integer, positive integer power, I can integrate by a u substitution, u equals x minus a. And that in integration gives me minus 1 over n minus 1 times x minus a to the n minus 1 plus a constant. My point is, we can do these integrals. Right? So far, so good? Oh, what else can we do? We can integrate a polynomial. Agree? You're like, yes, please make sure to test me on that. I'm not sure I understand. I really need some more accountability on that. Test me on integration of polynomials on the test. Please, 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 please. Right? Yes, okay. You're like, you don't, I'm really less certain if you put actual numbers there, though. It would be even a better test question if you put like a 7 here and a 6 here and maybe a 3 and a 1. None of these pesky arbitrary constants like you're using here. Right? Sorry. But we know more. If we have division by an, this is, so what we're looking at here is an irreducible quadratic. Do you guys know what an irreducible quadratic is? No. So Dr. Skabordis told me that yesterday he solved the quadratic equation from base principles for his class, and I didn't do it for the earlier section, but I think I'm going to do it for you guys. Somewhat off the beaten track from our current conversation, but it's a conversation we should have at some point. It's a conversation you should have had before in college algebra or something. But if we have ax squared plus bx plus c equals to 0, how can you solve that? In general, here's what you do. I have a times x squared plus b over a times x plus c over a equals to 0, right? And we're assuming a is not equal to 0. So then what? What's my next step? I can divide by a, right? And so I have x plus b over 2a, quantity squared. Then what? Minus b squared over 4a squared plus c over a. What did I do? I completed the square, right? And then what I can do is I can say, aha, well that's really x plus b over 2a. And different folks will go different directions at this point, but I'm going to go ahead and do it like this. So that's, let's say I got myself a b squared minus 4ac divided by 4a squared. Right? Just bring it to the other side. And if I have a quantity squared is equal to another quantity, what are the possibilities? Right? Either this is, if this is negative, that says that there are no real solutions, right? If it's 0, we get a double solution. We get the same solution twice. And if it's positive, we get 2 solutions. Right? Because if you have a real number squared, it can't be negative. It could be 0. It could be positive. But it can't be negative. If it's negative, that corresponds to the case that there are no real solutions, right? But anyway, taking the square root of both sides and abusing a little complex variables here, we get plus or minus the square root of b squared minus 4ac divided by 2a. Technically, I should have absolute value of a there, but you can lump that into the plus or minus logically. And so here you go. X is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. You may recognize this. This is the quadratic formula, right? Something you should be able to derive, right? Because if you can complete the square, you can derive it, just like this. So there are these three cases, right? In the case that, let's see here. So we can always, I guess you can always go back up to here in view of this, and you can do, this is really a times what? Times x minus, let's say, lambda 1 times x minus lambda 2. Well, let me say plus minus. So say that these are lambda. But that's only, that doesn't give you a real factorization in which case. If that b squared minus 4ac over 4a squared is negative, you don't get a real factorization, right? In that case, the quadratic is said to be irreducible, or some people call it prime. It doesn't factor over the reals. Just to give you a simple example, for example, x squared plus 1, right? This would be something like x squared plus 2x plus 1. And here would be something like x squared plus 3x plus 2, right? This is x plus 1 quantity squared. This is x plus I times x minus I. We don't usually, unless you're allowing complex factorizations, you have to say it can't be factored, right? X squared plus 1 can only be factored over the complex numbers. It can't be factored over the real numbers. And this one, well, this is kind of your more happy place, right? This is x plus 2 times x plus 1, right? Those are the three cases. Okay. All right. Well, now that I've got that out of my system, it's important because we keep coming back to the question of things that involve quadratic factors. It's important for you to have ownership over what are the different possibilities and how they're related to the problem of solving the equation ax squared plus bx plus c equals 0, right? So, any questions? Okay, so getting back on track. I blame Dr. Skambordis for that. He tempted me to do it yesterday. It's all his fault. So we can also do this integral, right? So this is one of those quadratics you can't factor. If it's a sum of squares, there's no way to factor that over the reals. It's an irreducible quadratic. But we can solve that by trig substitution. It's a tangent substitution. I'll let x minus alpha equal to beta tangent theta, right? So then x minus alpha squared plus beta squared just works out to beta squared secant squared theta. Lo and behold, the secant squareds cancel, and we're just left with the integral of d theta. So this integrates to 1 over beta inverse tangent of x minus alpha over beta plus a constant. Yes, sir?
I don't mean to be a slow man, but can you start from the beginning one more time, please?
Here?
Yeah.
So how do we do this integral? Basically with trig substitution, right? I have a sum of squares, which means I can use a tangent substitution. So I set x minus alpha equal to beta tangent theta. Then x minus alpha squared plus beta squared would be like beta squared tangent squared theta plus beta squared. That simplifies to just beta squared secant squared theta. So the denominator becomes just that, right? And then I also have to change the measure, the dx. So when I differentiate this, I get beta secant squared theta d theta, which I put here. Secant squareds cancel. And beta over beta squared is 1 over beta. And then I integrate. And then I undo the substitution, and there you have it. There's the integral. Oh, by the way, if we had a similar integral where we had like a and x minus alpha upstairs, we could also do this kind of integral, right? If I have x minus alpha divided by an irreducible quadratic like so, we can also do this kind of integral by a u equals x minus alpha squared plus beta squared substitution, right? See, because du is what? It's 2 times x minus alpha dx. So that this is really 1/2 du. And so there you have it. If you have something of this form, we can also integrate it, and we get natural log of the square root of the quadratic plus a constant. Right? Ah, but there's more. If we took a quadratic, right, an irreducible quadratic, a prime quadratic if you like, and we raised it to the nth power, where n is some power greater than or equal to 2, I can make the same trig substitution as I did up on the last one. And when I do that, I get still dx is beta secant squared. What's underlined in blue is beta secant squared, beta squared secant squared. So when I raise that, this is the same as beta secant to the theta to the 2n power. And when I simplify this, I just have the cosine to the 2 times n minus 1 power theta d theta. Don't worry, I'm not actually going to work these out. My point to you is that it doesn't matter if n is equal to 2 or 3 or 4 or 5 or whatever. In principle, we can do those, right? It's a pain, but this is well within our grasp. We can do these integrals. Consequently, we can integrate this function for like a square, a cube, a fourth, whatever. Yes, sir?
For that first part, should you go like the absolute value bars when you know?
So can anybody tell him why I don't need absolute value bars there? He's asking why didn't I put absolute value bar here and here, right? Yes, sir? Because it's a sum. Yeah, it's a sum of two squares, and I'm assuming that beta is non-zero, so it's necessarily positive, that quantity. So I can omit the absolute value there. Yeah, and I pulled the half inside to give the square root. Yeah. Good question. Other questions? So I'm telling you this because I want to encourage you to realize that we can do that. That said, I don't really want to do this. I just want to show you we could if we needed to. It's right there, right? And by the way, if I replace the denominator here with the nth power, I can still make this u substitution just the same and do those kinds of integrals as well, right? All right, so what I'm trying to tell you is all of these integrals we own. We can do these. Could be a pain, but we can do them, right? And everything you're looking at here, you're looking at a rational function where the degree of the denominator is strictly larger than the degree of the numerator. The things I'm looking at here are, strictly speaking, the basic proper rational functions. All right? So in particular, basic proper rational functions are things like 1 over x minus a, 1 over x minus a squared, 1 over x minus a cubed. You keep going. Anything like that's a basic proper rational function. 1 over an irreducible quadratic. 1 over irreducible quadratic squared, right? Also basic proper rational functions. And to be clear, I could also throw in things like, to be clear, I should say something like, c1 plus c2 times x minus alpha. Those are also basic proper rational functions for any values of b1 and b2, c1 and c2. All right? So what? Well, there's this process that says, and there's basically, there's something called partial fractions decomposition. And this is the algebra fact. Any rational function permits a partial fractions decomposition, or a partial fractal decomposition, if you like. That is, I can write any polynomial as, any rational function rather, p of x over q of x. I can write it as a polynomial plus a sum of basic proper rational functions. And I really should say, there's a word missing there. weighted sum. You could say it as a linear combination of basic proper rational functions would be a better, more educated way of saying that. So what's the process? Let me just outline the process for you. Step one is you're given f of x equals to p of x over q of x. All right, and you do long division if need be to write f of x is equal to, say, something like m of x plus r of x over q of x. The r of x over q of x, this will be a proper rational function in the sense that the degree of r of x will be strictly less than the degree of q of x. Step number one. Step number two. Step number two in this process is completely factor q of x over the reals. So what that looks like is something like this. Q of x can be rewritten as some constant, whatever, we call it, I don't know, c, some number c, and then you've got things that are like x minus a1 to the, say, m1 power, right, so forth and so on, x minus a2 to the m2 power, and this goes on. And then eventually you have things like irreducible quadratics, x minus, say, alpha 1 quantity squared plus beta 1 squared to the, say, n1 power. And these go on. You got so many of these. All right, eventually, but you have a product of possibly repeated linear factors and possibly repeated quadratic factors. Okay? And here's the deal. For something like x minus a, say, to the m power, you put something like this. You put a1 over x minus a plus a2 over x minus a squared plus da 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 plus a m over x minus a to the m power. Okay. This put I'm talking about, I will make more explicit in the examples. All right. I'm being somewhat vague when I say you put. For the quadratic, if I have x minus alpha squared plus beta squared, and I have that to the, say, the n power, you put a1 plus b1 times x minus alpha divided by x minus alpha quantity squared plus beta squared plus a2 plus b2 times x minus alpha divided by x minus alpha squared plus beta squared quantity squared plus dot 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 plus a to the n, a sub n plus b sub n times x minus alpha over x minus alpha squared plus beta squared, this time to the nth power. And you have to put these many, these kinds of expansions corresponding to each factor that appears in the denominator. Here, let's try to, let me show you an example of the setup before I actually, this is actually an honest to goodness example I'll work through here in a second. We'll get to that. before I actually work out the details for you for a problem, let's just try to set one up together. Suppose I have something like, oh, let me give you a second to catch up with your writing. It's a lot to write. By the way, there's what I just wrote in purple is on page 424 and 426 of your text. There's little blue boxes that capture these ideas just the same. Maybe with slightly different letters, but the spirit is also there of this comment. What's that? 424, 426, I think. Section 8.5. All right, let's see here. What if we have something like, so here's the example setup, but do not make explicit the undetermined coefficients for the partial fractions decomposition of, and here's what we'll work on, f of x equals to, let's say, x squared plus 3x minus 7 divided by x squared plus 3x plus 2 times x squared minus 1 times x squared plus 4x plus 5, like that. All right, good news. Step 1, oh, by the way, I forgot step 3. Step 3, integrate. Step 3 is to find values for A1, etc., AM, and so forth by algebra. And integrate. I mean, that's our ultimate goal, is to integrate the rational function. All right. But my point to you is this process, thankfully, we don't have to do step 1 for this example, right? Because that's already a proper rational function. The degree of the numerator is 2. The degree of the denominator is what? 6. Oh, you get 8? Oh, 6. Okay, good. So 1 is done. But we got to completely factor the denominator. So how do we do that? I got what? I've got x plus 1. I'm going to save some writing here if you don't mind. You're like, yay, less writing. Where's my... I thought I had a red marker. Where'd it go? Oh, duh. All right, so this is x plus 1 times x plus 2, right? X squared minus 1, what's that? Yeah. And how about that? That's one of my favorite irreducible quadratics. That's x plus 2 quantity squared plus 1. You see, that one can't be factored. So what we have, right, is we've got ourselves, let's see here, I'm gonna do x minus 1. I'll put that one first. No particular reason. And then I've got x plus 2. And then I've got x plus 1 squared, right? And then I've got this x plus 2 quantity squared plus 1. All right? Now, partial fractions decomposition says you can rewrite this rational function as a sum of basic rational functions as follows. You can write this instead as a over x minus 1 plus b over x plus 2 plus c over x plus 1 plus d over x plus 1 quantity squared. All right, plus c plus d times x plus 2 over x plus 2 quantity squared plus 1. Oh, I'm sorry. Not c and d on the last one. What should these be? E and f. I'm going to have to go back to kindergarten. I don't know my alphabet. Like A, B, C, D, C, D. No, sorry.
Why is there a c over x plus 1 when there's x plus 1?
That is the partial fractions decomposition. It's necessary. So, you'll see. I'll try to find an example of that. I don't know if we have time today for it. But to answer your question properly, I would show you an example where it's required. I guess I can... Oh, let me come back to your question just a second here. So that's it. Now, there's some things to observe. A, B, C, D, E, F. How many is that? 6. That's not an accident that this is a 6th order polynomial in the denominator. If your partial fractions decomposition is correct, you will have as many undetermined coefficients in the expansion as the degree of the denominator, assuming that you have done step 1 in the process correctly. This is an inevitability. Now, I can bump this example up a notch. What would happen if instead of that irreducible quadratic appearing linearly, what happens if I put a square here? What happens? All we have to do is add another term. G plus h times x plus 2 over x plus 2 quantity squared plus 1 quantity squared. If you understand this example, you're about 90% of the way to understanding this general advice. Yep.
Is that just a what if, or was that actually part of the process?
If I add what's in purple to the left-hand side, I must also add what's in purple to the right-hand side. Or you could delete the purple. Get an appropriate pair of glasses with a purple filter. Set it to 0. Here, I'm going to work backwards. So you ask me, why is it that I need the x plus 1, right? So let's try this out. 1 over x plus 1 plus 2 over x plus 1 squared, right? What's this give us? Right. So what we have is x plus 3 over x plus 1 squared. So there you have it. There's a rational function which has x plus 1 squared in the denominator, and yet the partial fractions requires 1 over x plus 1. What is partial fractions? It's undoing a common denominator. That's what's going on. I mean, you already know. You know how to do this direction, right? We're just trying to teach you this direction. That requires a little bit more imagination, and that's what this is. This actually is the possibilities of undoing it. And you just haven't thought much about that reverse question, so your intuition might be wrong. Nothing wrong with that, it's just, I'm not used to this new schedule yet. When does this class end? What time do we start? 10:10. All right. There used to be a delicious Chinese buffet restaurant I used to eat at in Raleigh called 1010's. It was good. It's now changed its name. It's close to the apartment I had. It was an interesting apartment. There was there's a Mexican gang somewhere in there. They used to like to take their bikes out into the street and do wheelies at night, like 3, burn the rubber up, you know. And then, like, the guy who lived above me, I'm pretty sure was a drug dealer. I mean, we can't be sure, but generically speaking, when you come home, you shine your lights. Like, we were kind of in a corner lot, right? As like it was one of these apartment complexes, small apartment complexes. And there'd be like a pair of people standing in the corner. The lights would hit them, and then like one would go running that way, the other one would go running that way. It's like, that's odd. Once I forget it was me or my brother. One of us took the trash out at like 2 in the morning, and it was raining. And there's just a guy standing outside, just standing outside by the trash, and here, I'll take it for you. Thanks. It's important to this story that he was not smoking. I mean, he was just waiting for somebody to show up, I guess. I don't know. I never had any problems, really. There was another grad student who had his apartment broke into, and somebody thought he was somebody else, and they beat him to... He took him months to recover, because I guess they probably thought he had drugs or something, but he didn't. I don't know. Raleigh is generally safe, though. I mean, it's not... I lived in Duke. I lived in an apartment not far from Duke for a while. That was a little bit scarier. Like, bikes get stolen in the daytime there. It's not good. But anyway, I digress. Oh, so here's an example. So how would you integrate x over x times x squared minus 1? So what you do is you take it. Okay, thankfully we haven't had to deal with step 1 in the process. I'll deal with that next class. I factor the denominator, right? And then, so I've got a over x plus b over x plus 1 plus c over x minus 1. That's my partial fractions decomposition. I need to find a, b, and c this time. I'm actually trying to complete the process. This is not a partial example like the last one. So what I do, to get from here, how do I get from this equation to this down here? What do? I did what? I multiply by x times x plus 1 times x minus 1 and cancel appropriate factors, right? What do I mean cancel appropriate factors? So like, with the a term, what canceled out? I have a over x, right? When I multiply a over x times x plus 1 times x minus 1, x over x cancels, and I'm just left with x minus 1 times x plus 1. Do you guys see that? If you don't see it, just write it out, and then you'll see it. It's not a big deal. And then for the b term, x plus 1 cancels x plus 1. It just leaves me x times x minus 1. And then for the c term, the x minus 1 cancels, and I'm left with x times x plus 1. So I've got this equation. It's actually a quadratic equation in x, and it's got 3 undetermined coefficients, a, b, and c. I think the easiest way to solve this is to plug in values for x. We'll see that sometimes plugging in values is helpful. Other times just working out equating coefficients is helpful. Next week, we'll see. Monday, really. But if I put x equal to 0, what happens? See that? This term is gone. That term is gone, right? 0, 0. I'm just left with a times minus 1 times 1. So I get 1 equals to minus a when I put in x equal to 0. Question? What if I put in x equals to 1? See, this is 0, right? That's 0. This, 1 times 2 is 2. So I get 1 equals 2c. C is equal to a half. Put in x equals to minus 1. That time, that term is 0. This term is 0. I'm just left with the b term. I get minus 1 times minus 2, which is 2. I get 1 equals 2b, so b is a half. So what I've shown is 1 over x times x squared minus 1 is in fact reverse common denominator. Sorry, the partial fraction decomposition. Let me talk like an intelligent person. Let me pretend for a minute. Is this, right? And that is wonderful because I can stone cold integrate that. That's natural log absolute value of x, 1/2 natural log of absolute value of x plus 1, 1/2 natural log of absolute value of x minus 1 plus constant. And this, folks, is partial fractions. It's the process simply of taking the rational function, breaking it into basic rational functions, which you then can integrate. The fun is really in this part, more generally. This is an easy example. I guess some of this is also fun. I don't know. But that's really trig substitution. Well, with that, I wish you a good weekend. Thanks, guys.